So good afternoon and welcome to another lecture for calculus. Before I start with the topics of this week, let me do a few organizational things. First of all, on Canvas you can leave questions. As you know, there is this option to post questions before the lecture and I'll try to address them here. Now, since I did answer the questions, the old questions that were there last week, I made a new round of questions. So the old questions you won't see immediately. They're not gone, but I've answered them. So I moved them away so we have a clearer overview of the open questions. So feel free to post questions there now and I'll have a look maybe in the break. I'm not sure. But at least before Wednesday. And if you have questions that you would like me to do, so if there's problems in the homework and you haven't got a clue and you don't understand and also your fellow students cannot help you, then I'm happy to do those on Wednesday morning. If you have any requests now at this moment in time, put them in the live chat on YouTube, and that's easier for me to check during the break so I can see the chat while we're at it, so I can immediately address those questions there. Now, as you know, this is week 4. There is a total of 8 weeks of lectures, with the distinction that we do not do new stuff in week 8. So in principle, all the new stuff is weeks 1 up till 7. And then week 8 is for exam preparation. And as you also know, so this is week 4. Next week, in week 5, there is going to be the midterm. And there's already some people getting a bit nervous about the midterm. So you will get more information there. But for now, let me already tell you that the material there is the material from week 1 till 3. So basically everything we've seen up to today. During the test, there will be proctoring, which means that people will watch you via the webcam on your computer to see whether you are really doing this without any help. As such, you can only have blank paper and a pen, so no calculator. And you should show, you're being asked, so it will be clear, but you have to show the paper in advance. So also before the exam, do not write anything on the exam paper. And then during the exam, you can write it down. And basically you have 2 options of answering questions. You can either type, like you can also do for your homework. You can also upload photos and you can upload those with your mobile phone. And at the end of the exam, there will be some time for that. Also, people who have some extension, time extension because of dyslexia, you will have that during the test. And again, that will be automatically done. So you will get more details on that. Also, as you know, you don't have to know all the formulas by heart. We will give you some formulas on a separate sheet of paper. And we already put up some old exams, so you know which types of questions we ask. And then in the old exams, you can also see the formulas that we will provide. So that doesn't change. That is the same as it was in the previous years. And we will have a look there. You can have a look there in the old exam questions. So there is an old exam on Ans Delft, which is the environment that you use for your homework and that you'll also be using for the midterm test. There is also, if you look at the Canvas site for the course and then in study materials, then you will see that there is the midterm for both architecture and industrial design from last year. You can look at both of those tests. The single reason that we have different tests for architecture and industrial design was that we couldn't take the exam at the same moment in time last year. As you may have seen, architecture has a different time slot and we have Monday morning and Thursday, and we are Monday afternoon and Wednesday morning. So that's the reason there are separate tests, but you can look at both of them. And in the industrial design test, you will also see the rubber ball question that I have mentioned earlier during lectures. One thing more, I got several questions, which is great, and you can ask them like in Canvas or in the chat now. I'm going to look a bit later. I see some questions popping up. And also via email. Now, if you have questions, please make clear what it's about. So if it's on slides, my slides are all numbered. There is a number at the lower left corner. So if you look at the lower left corner, then tell me which slide you're asking a question about. If you have something about a question in the book or the online test or online practice questions, make a screenshot. That helps great. Or make a picture. It helps a lot if you also provide me with the question. I don't have to look it up myself because that takes more time. So if you ask me something or your tutor, repeat the question and take a photo of whatever you were trying to do. Okay? So that is the organizational bits and pieces. Let me check now in the live chat. I'm getting also, I need glasses for that. So again, there was a question on the chain rule, which may be formulated a bit differently in the book than what you're used to. So again, all the mathematics that you know in high school, that's still valid. It's not like we're doing completely different mathematics and you should forget about what you have done before. If you have to do the chain rule and you prefer a different notation or a different way to write it down, just as long as it's clear, that's fine. You don't have to use our notation. As long as it's mathematically correct and it's clear to whoever is marking your paper what you're doing there. So if you make some miracle steps, then well, that may be hard to mark for us. But if you clearly write down your way of reasoning, then if it's correct, you get full credits for that. So there is also a question about the paper. So either you type in your answers to the questions just online, or if you want to use scratch paper, and it's also good if you answer the questions online that you have a little bit of scratch paper, you have to provide that yourself. So make sure you have some blank paper. We're not going to send you paper, right? Because it's going to be at home. So for the midterm that you will get more information. So I'm not going into all the details there right now, but we will provide you with more information. In principle, you have to write down the intermediate steps. So we will ask you for your solutions, but we'll provide you with more information on the test there. So for now, I would like to move to the week 4 material. So let's see. Let's switch to the slides. And this first picture that you see is, of course, the Netherlands, and then in spring when the tulips are blossoming. And what you see here is related to what we will be doing during this week. And I think if you look at the contents of week 4, it should not be terribly difficult. I think this is one of the easier weeks related to the rest of the course. So what we'll be looking at is differentiation. And you know a lot about differentiation already. But in particular, how we can use that to find maximum, minimum, stuff like that. And we've got a couple of nice examples for that. So I think you may like that. So let's have a little outlook. So we are covering some sections from chapter 2 and 3 in the book. And we go back to the initial chapter again. And one of the things that I will be talking about, and this is just one example, there's going to be a couple of them, is maximizing the area for a given amount of fencing. So I'll start with an introductory example there to hopefully help you understand what this is useful for, how you can use it, and also something that you may be able to solve if you think about it for a very long time. You can translate into a very simple question once you have the mathematics, and then it's very easy to find a solution. So that will be in a minute. And below here you see a list of all the topics. So I'm not going through all of them, but it's basically differentiation, also of the standard functions that we've already met, like sine, cosine, tangent, and how we can use it. So how can we find maximum, minimum of a function? And a little bit, and that's a bit more technical, that's probably Wednesday, is inverse functions. So as you know, you have functions. You take an x and you get a y. That's what a function does. Can you go back? Can you also find the inverse function, which given the y gives you the original x back? So sometimes you can do that, sometimes not. And we'll get to talk about that later on, maybe today, otherwise on Wednesday. So let's first look at a little example. So the example here is, say that you have 40 meters of fencing. So you want to build a fence, and with that fence you would like to enclose a rectangular area. So for instance, if you have 40 meters, what you could do is make a side of 5 meters and a side of 15 meters. Now, if you want to build a fence here and here, you need 5 plus 15 is 20 meters. And then if you want to have a rectangular area, you see that indeed we have 40 meters of fencing, that we used all of it. Okay. Now, next. What you could also do, I mean, this is not the only way you could do that, right? So here we have chosen to use 7.5 meters in this direction, 12.5 in that direction. Again, together it's 20. So the full rectangle uses 40 meters. And if you like more symmetry, then you could even build a square. And if you build a square with a side of 10 meters, you see that in total we use 4 times 10 is 40 meters. Now, this is all different ways of using 40 meters of fencing. So that's a given. We have 40 meters and we're going to be using all of it. And you see that there's different ways that you could do this. Now, there is a difference here because, well, in principle, I mean, if you're going to keep sheep or whatever, you would like the area to be maximal given the amount of fencing that you have. So if you look here, you can easily compute that, of course, because the area is the width times the height, or the width times the length. So here it's 5 times 15 meters, and we have 75 square meters of, say, grass in there. Now, for the second one, you can also compute it. If you multiply them, you see that you get 93.75 square meters. And here, apparently this one is maximum of these 3 possibilities. So here we have 100 square meters. Now, say that we would like to have maximum area. So given a fixed amount of fencing, we want the maximum possible area for our little area for the sheep. So what is the best solution? Now, if you try to do this by hand, if you're just going to plot a couple of them like I did here, you will probably soon figure out that this here is the best that you can do. But is that also the best solution? Or is there maybe a solution that we missed and that we just didn't think of? Now, how can we do this? So let's try to capture this into mathematical equations and see if we can use our knowledge of calculus so far to answer this question. What is the best possible way to do this? So what I'm going to do is I'm going to look at any rectangular area. So I'm going to say that this side has a width of x meters, this side is y meters, and then if I have x meters plus y meters, then the parameter, so here I need x meters, here I need y meters, here again x, here again y. So the parameter, in Dutch language, the omtrek of this area, the amount of fencing that you will be needing, I denoted it p here because in English it's parameter, is 2x plus 2y. And then the area that we get is of course x times y in square meters. So you see that the area is in square meters and the parameter is in meters. Now the question that we just had on the previous slide is given 40 meters of fencing. So the p-value, the parameter, is given. We have 40 meters of fencing. Now, and the trick that we will be using time and time again in this week when we are trying to solve these types of problems is that we say, well, we have 40 meters. So I know that 2x plus 2y equals 40. That means that I cannot choose both x and y freely. If I have chosen an amount of x, then y is fixed. And using that, I can get rid of one of the variables, and then I have, in a minute, a function of one variable and functions of one variable. Well, that's the whole calculus that we are talking about. And we can do all kinds of stuff with functions of one variable. So here we have 2x plus 2y equals 40. So 2y is 40 minus 2x. So y is 20 minus x. So if we now compute the best value for x, then we know the corresponding y. We can always compute that. So what is the best value for x? Well, the question is that we want to maximize the area. So this value here, a is x times y, we want to have the largest possible value there. Now, y I have just found equals 20 minus x. So I can now express the area in terms of x only. So let's do that. So the area is x times y is x times 20 minus x is 20x minus x squared. And in principle, the question is now answered because you can plot this, right? You can take your graphing calculator or you can use some computer software and you can plot this function and you can see where it is maximal. So how do you find the maximum using mathematics? Well, we use a derivative. That's what we have seen last week. So what we are going to do is we define a new function f of x, 20x minus x squared. We compute the first derivative. And we know that if you have a maximum of a function, then the tangent line should be horizontal. So I'm going to look for points where this f prime function, f prime of x, where the first derivative equals 0. And that is a potential maximum. Could also be a minimum, right? So let's see. F prime of x equals 0. That's the same as 20 minus 2x equals 0. That means that x should be equal to 10. And now I'm going to check that indeed it's a maximum. So we have here a sign chart of f prime. So below is x, above is f prime. And for x equals 10, f prime equals 0. And to the left of 10, for x value smaller than 10, f prime is positive. I can easily substitute, for instance, x equals 0. If you plug in an x value, say here to the right somewhere, say 100, then you can easily see that this becomes negative. So we get negative here. Now, if f prime is positive, I know that the function itself is increasing, is going up. And if f prime is negative, I know that the function itself is going down. So what you read here from this sign chart is that the function is going up and is then going down again. So we see that indeed there is a tangent line, a horizontal tangent line here, and that is for x equals 10. So we have found a local maximum. The local maximum is f of 10, so the area is 100 square meters, and that is for x equals 10 meters. So this is, in a sense, the proof that you cannot do better. So given 40 meters of fencing, the best you can do, the maximum area that you can enclose using a rectangular form, is a square with sides equal to 10 meters. So basically what we intuitively found on the previous slide, that from those different configurations, probably the square was the best one. This is the proof that this is indeed true. And this is how you can find it. And this is quite limited, but it covers the basic idea for a number of questions that you will see in the problems from the book. And also I'll do a couple more today. So that was the introductory example, and hopefully that you find, okay, this is interesting and this is where you can use derivatives for, so you can find maxima. Now, the next topic in the book is from chapter 2, is a bit on higher order derivatives. So, for instance, if s of t is distance as a function of time, so maybe you recall that when I started talking about derivatives, I was talking about traveling by train, and I said you have t, and then you can do s of t here, and then if you're traveling by train, you get something like, for instance, this here, shaped like this. And we have seen that if you take the first derivative, that you have the velocity of the train. If you differentiate once more, then you get the acceleration of the train. So acceleration, a of t. Let's see. Maybe you recall from physics. That is the first derivative of velocity. Now velocity is the derivative of s, displacement. And this is, well, you can write it like this. Oh, sorry, I made a little typo here. This should, of course, be a t. And this is just different notations to say that you have to differentiate s of t twice with respect to t, with respect to time. So that notation is also here on the slide. So a of t is the derivative of velocity, so we get v prime. And that means that it is the second derivative of the displacement, like this. So in general, if you have a function like we usually write it, so if you have a function y is f of x, what we normally do, then we have two different types of notations. Let me get a sip of water because my throat is itching. That's hopefully better. So the normal notation, f prime, f double. And it gets a bit difficult if you have like a higher derivative. So here you see the third derivative, but that's also written like this. So sometimes we also do a 3 and in between brackets, just to distinguish it from having something to the power 3. That means something different. So if you want to make that clear in notation, we write little brackets around it or parentheses. You have this alternative notation with df, dx, and so on. So that's just notation wise. Then a little bit on derivatives. You already know this, I just put it here for reference. If you differentiate the sine function, you get the cosine. If you differentiate the cosine, you get minus the sine. And the tangent, you could use the chain rule or the quotient rule there. Tangent is sine over cosine. If you differentiate, you get 1 over cosine squared. We talked about limits last week, and I already tried to convince you that this function here, well, as you see, it's not defined for x equals 0 because we would get division by 0. But if you make the plot, it looks like this here. And in particular, around 0, you see that the function values are very close to 1. And indeed, you can prove, and I'm not going to prove that. There is a proof in the book, but I don't think it is very clear. That's one thing. And I don't think it adds a lot. So sometimes I will try and prove things if I think it helps you or it helps understand, or maybe it's just a thing of beauty. I don't think that proof is a thing of beauty, so I'm going to skip it. So you just have to learn by heart that if you have sine of x over x and you take the limit for x going to 0, you get 1. We will be talking, maybe you've seen that in high school already, about L'Hopital's theorem. And you can also prove this using L'Hopital's theorem, and then you don't have to learn it by heart. But basically, the interpretation is, you could say, and that's just a bit of extra, but you could say that sine of x is approximately equal to x if x is very small. So what does that mean? Very close to 0. So if you have very, very tiny values of x, x is 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, then the sine of x is almost equal to x. And that's basically what the theorem tells you. Because this theorem tells you if you let x go to 0, then if you divide sine of x over x, you get 1. That means that they're approximately the same value. Okay? Now, how can you use that? Well, so I hope you recall this thing. And for later reference, I'm going to write it down using a different letter. So you could also say, well, this also means that the limit of, say, u goes to 0, sine of u over u equals 1. The letter is not important, right? You can pick your favorite letter here. Now, I have a couple of questions here, and you should have a look at them and see if you can solve them. They are in line with the online practice and the online test and also the assignments in the book, but they shouldn't be very difficult for you. I would like to do these last two because they use a trick, and you should have seen that trick once. So first, question 6 here. Question 6 says, or is you're being asked for the limit of x going to 0, sine of 3x over x. And now the main idea here is, if I write it in green below, that the limit of u going to 0, sine of u over u equals 1. But you see that, well, here I have a 3x and here I have an x. And in the standard limit that you can use to solve this question, we have u and u. So they should be the same. You should have the same expressions there. Now, the trick, and hopefully if you have seen it once, you're going to recall how this works, is that you say, well, this is the same as the limit. X is going to 0, sine of 3x. And now I would like there to be a 3x here. Because if I have a 3x there, I could call that u, and then I really have sine of u over u. But I cannot simply write a 3 in the denominator without also writing a 3 in the numerator. So now I have written 3 in the numerator, 3 in the denominator, so I didn't change it. And this thing here, well, this first limit is going to 1 times 3. So apparently the whole limit goes to 3. And question 7 is along the same line, but here you have to use the same idea twice. So for question 7 we have the limit x is going to 0 sine 7x over tangent 2x. And still here you have to use the same idea. So you have to use the green standard limit that is on this slide. So, well, what I'm going to do, sine 7x times, well, the tangent is sine over cosine. Here I have 1 over the tangent, so I can write this thing as cosine 2x over sine 2x. And now what I would like to do is use the standard limit. So I'm going to write this as the limit x is going to 0 sine, so that doesn't go well, sine 7x over 7x, and I just added this 7x, so I have to compensate for that, times cosine 2x times, and then I have here sine 2x. And I would like to use the standard limit, so I'm going to write a 2x here. And now I have added all kinds of stuff, so I also need to compensate for that. So I'm going to add 7x over 2x here. And now what I've been doing is just adding stuff both in the numerator and denominator. So what you see here is that I didn't change it. I just wrote it in a way that is convenient for me. Because now what I have is I know that this thing here, well, this is of the type sine of u over u. So this will go to 1. This here, well, it is not sine of u over u, but it's that thing upside down. Well, if sine of u over u goes to 1, then we also have that the limit u is going to 0, u over sine of u. That is basically the limit u is going to 0, 1 over sine of u over u. And now we can use the standard limit. This is 1 over 1 equals 1. So you can also put that upside down. So what I try to convince you here, and hopefully I've managed, is that this thing will also go to 1. Now, the cosine is innocent. I can just plug in x equals 0. And this last thing, well, there is x both in numerator and denominator, so I can forget about that. So that is 7 over 2. So the whole bunch will go to 1 times 1 times 1 times 7 over 2, which equals 7 over 2. So that is how you can do these types of questions. So the idea about these questions, reacting to what is being said here in the chat room, the idea is that you try to use this as given. So this is true, and you don't have to prove or show it. You should try to rewrite the question that you're trying to solve. So these types of questions, using that this here is true. So that's how you do these types of questions. So the sine of something, and then over that same something, that will go to 1 for the something going to 0. Okay. Now let's go a little bit to what I was referring to before. So we are going to be using the derivative now. So let's see. I have plotted a function here, and I do not give the formula here yet. I'm just interested in the shape of the function. And if you look at it, and we are interested at this moment in time in maxima and minima, so you see that there is something like a maximum here, and there is something like a minimum here and here. And if we're only interested in the function on the given interval, so basically what you see here, then also here is like a kind of local minimum, and here is a kind of local maximum. So that's what we are going to make a bit more strict now. So a global maximum is when you have a maximum, and also if you look at the whole graph here, you see that nowhere else the function reaches this value. So it's like the maximum for all the values of the function that we consider. This thing here is called a local minimum, because if you look at the surroundings, for instance the area that I mark here, you see that it's a minimum. However, if you would look at the whole range, then you see that here, at this point, there is a minimum that's lower. So this thing is called a global minimum, and this thing is called a local minimum. So local is really if you're at a point and you look a little bit to the left, a little bit to the right, and then it's a minimum, that's a local minimum. So here we have a local max, and here we have a global minimum. Now, being in a point and looking a little bit to the left and to the right, that doesn't sound very mathematical. It is, but we have to formulate it a little bit differently. So the way you do that mathematically is that you say, well, say that we have a function that's defined on an interval a, b. Okay, fine. We take some point, and then we say that f of c is a global maximum of the function if f at c is bigger or equal f of x for all the x values that we consider. So we have this function on the interval a, b. That's our universe at this moment in time. That's the only area that we consider. And for every x value in that interval a, b, if we have this property for fc, it's a global maximum. Okay? And here in the picture you see a global maximum plotted. So if you now first go to global minimum, that's the same, but then the sign here is reversed. See? So that's the smallest for all the values that we consider. So those are easy. Now for the local one, what we do is that we say, well, here below is C. And now I'm going to consider an interval that contains C. So there is a little interval. It doesn't matter how large it is, just that it's an interval. So there's points to the left of C and points to the right of C. So there is a little interval around C here, like this. And it's an open interval, so I wrote little brackets, but let's do open circles. And that interval here, that is I. So I is, let's say, D, E. D is less than C is less than E. And we also have that A is less than D is less than B. So we have the whole interval AB. We take a point C and we shrink this interval to an interval DE. So we have a little open interval, and basically the only thing that we need is a few points to the left and a few points to the right. And then we talk about a local maximum if fc is bigger or equal fx, but then only for those x values in that open interval. So this is how you can capture in mathematical terms that you want to go a little bit to the left and a little bit to the right. So as you see in the picture, it's a local maximum because there is a true global maximum here. And if you look at the surroundings, the neighborhood of this point, there it's a maximum. So that's the main idea. And you can do something similar, of course, for a local minimum. So again, we have the point C here, and there should be an open interval around C. And on that smaller interval, we have that it's a minimum. Okay. Few remarks. I'm going to be talking about maximums and minimums all the time. Now, to capture both of these, we have extremum. So extremum is either a maximum or a minimum of a function. So that captures both of these situations. Then there's different ways to describe a global maximum. So global is the same as absolute. And local is also relative. So we have basically these pairs. So we have global and local. So local is in a small area, and global is the whole domain that we consider. And you can also talk about absolute or relative. And that is the same distinction, it's just different names. The only thing is that, I mean, both names are great. I think global local is maybe the most insightful because it immediately tells you what's happening there. The book mixes them, which I think is pretty horrible. I think the book uses global and relative, and I think that's really silly to do that because, well, global and local is like a pair, and absolute and relative. And what you see is that these things are not unique, right? My picture suggests that maybe a little bit, but if you look at the sine function, then you know that the sine function just keeps going up and down between 1 and -1. So there are a lot of x values for which the sine reaches its maximum. And similarly, there are a lot of values for which it reaches its minimum. What you also see is that a global maximum is always a local maximum too, but not the other way around. And similar for a minimum, of course. And there is a question in the chat box if there is more than global and local. These are the only differences we make. So a function can have a maximum, and when it has a maximum, it can be a global one, and then it's also a local one, or it can be a local maximum, and then it is not necessarily a global maximum. And there is no more flavors than those. Something special that I didn't tell yet is if the endpoints of the interval are included in the domain, then there can also be a local maximum and a local minimum. So here I said it's an open interval. If I would close the interval and b would be part of the domain, then the function would have a local maximum at the right-hand side too, at the right side of the interval. So that's interesting. So we have maxima, we have minima, and we can make a distinction between global and local. Okay, right. So if I now give you a function, how can you find such an extreme? That's an interesting question because you want to minimize your costs, you want to maximize your profits, you want to maximize area maybe, like we did in the introductory example. So given a function of one variable, how can we find maxima and minima? So let's see. First, if a function is continuous, there is continuous again, so that's what we needed last week for, then you know that the function has an absolute maximum and absolute minimum on a, b. So that is not immediately obvious. Intuitively, you probably find that it holds true. So you have a function, it is on a fixed interval, the endpoints are part of your domain, and then you plot a function. And then, of course, there is a maximum because, well, we have a situation like this. So we have an x-axis, we have a y-axis, we have an interval a, b. Well, this function needs to depart somewhere. It needs to arrive somewhere. And it's continuous. So continuous means when we draw it, we cannot lift our pens from the paper. So I'm going to start here and then I'm can do all kinds of weird stuff. And then I have to end up there. And as you can immediately see from this picture, you see, well, here is like a global minimum. And you also see that here is a global maximum. And probably here at this point is a local maximum. Do I have all of them like this? Well, probably if my sketch, oh, here at the very left, we have a local minimum. Okay. So that concludes, I think, here what we have for extrema. But you see that intuitively, if you have a continuous function, you're leaving somewhere. You have to arrive somewhere. You can do all kinds of weird stuff along the way, but you cannot have jumps. You cannot lift your pen from the paper. It means that there has to be a global maximum and a global minimum. Maybe that's the only things you have. So if you have a function that leaves here and enters there, and if you just draw a straight line, you see that there is one global minimum, and one global maximum, and then we're done. There is nothing else going on there. If the function is a bit more creative than a straight line, okay, you can see other things can happen. But if there is no jumps, well, then we cannot. It has to be like this. Okay. The other thing that we have is that a function has a local extremum. So either maximum or minimum, local, not necessarily global. It can be local. And say that happens at x equals c, so some value there. Then it says here that two things can happen. Either the function has a horizontal tangent line, so that's what we've already seen last week, and that's the situation you see here. So the tangent line, the black line, is horizontal. Or it can also happen f prime of c is undefined, and here is our absolute value function again, and you see that at the origin there is a minimum. For x equals 0 there is a minimum, but the function does not have a derivative there. So these things, they are basically going to give us candidates for extrema. If you give me a function, I can differentiate it. I can check where the derivative equals either 0 or where it does not exist, where it's undefined. And those are places where you could potentially have an extremum. So candidate points for extrema. So to give that a name, again, because you don't want to say all the time like, well, the derivative equals 0 or it is undefined. So we are going to call that critical points. So a value is called a critical point if the derivative either equals 0 or it is undefined. And they are candidates for maxima and minima, sorry. So if a function has an extremum, then it is a critical point, not necessarily the other way around. So there is an arrow here and it doesn't point in both directions. It only points from left to right. And what can happen? Well, what can happen is this. You could have something like this. This is something like x to the power of 3. And you see that if you plot this, that it has a horizontal derivative. But you see that if you go a little bit to the left, you get smaller values. If you go a little bit to the right, you get bigger values. So it's not a maximum. And it's not a minimum either. It's not an extremum. It is called an inflection point. And in Dutch language, that's called buigpunt. Because the graph starts going in the other direction here. So I see that it's time for a little break here. So let's break up for 15 minutes and I'll continue lecturing at 14:30. And then I will also have a look at the questions in the chat box and I will try to answer them. So I'll see you in a bit. So let's start again. And I have seen a couple of excellent questions in the chat box on YouTube in the meantime. One of them is that if you have, so what I've just been using is that this thing also equals 1. And of course, the standard limit says that so the person asking in the chat room said, well, here we have u everywhere, but here in the top limit there is an x, whereas there's 3x here. So the idea is that if x goes to 0, 3x goes to 0. So if you like, what you could do is that you could say, well, this is the same, and what I do here, I'm going to set u equal to 3x, and then if x goes to 0, then 3x also goes to 0, so u goes to 0. So I could write this then as the limit of u going to 0 sine of u over u. So even though u is not the same as x, but it equals 3x, because we're talking about limits, if x goes to 0, also 3x goes to 0. So that's what I implicitly used there without writing it down. Another question that popped up there is, well, we're talking about maximum, minimum, global maximum, global minimum, local, and so on. What if you have the function y equals a constant, let's say y equals 2, and I'm going to consider it, for instance, on the interval from 1 up till 4. So what happens here with respect to maximum, minimum, global, local, and so on? Well, to answer that, let's go back a couple of slides. So let's go back to the definition here. So let's see. Okay, let's take this slide here. And now let's imagine that we're talking about this function that I just plotted. So we have the function that is y equals 2 on a certain interval. The interval doesn't really matter. So let's do it again from A to B. Now, if you look at the definitions here, so for instance, for a global maximum, it says that fc is bigger equal fx for all x's there. So what you see is whichever value you pick in this interval a, b, this is true. So indeed, every single x value or every single c, so if you pick some, let c in the interval from a to b, then for our example now, let's wipe this here because it's confusing. Then f of c equals 2. In fact, f of x equals 2 for all x in the interval from a to b. So basically what you see is if your function is a horizontal line, is constant, then every c in the interval ab, whatever interval we're looking at, it is a global maximum, it is also a global minimum, it is a local maximum, and it is a local minimum. So they all collapse here. If you have a horizontal line, all these things collapse. So it has maxima, minima everywhere. So that's a kind of extreme case, but sometimes it helps to look at those types of cases here. Okay. So I'm going to leave it here for the questions, and I'm going to check later and possibly come back to those on Wednesday. It is also great to see other students helping other students, so that's perfectly fine with me. I like that. Okay, so this is where we were. So the last question that we had before the break is how can you actually find them? So given a function, we have y is f of x, it's given, and we're trying to find the extrema. So first, a recipe to find global extrema, so global maximum, global minimum. How does that work? That's what we're usually interested in for a function. So what we do is first we compute the derivative. Then we look at the critical points. So where does the derivative equal 0 and where does the derivative not exist, where it is undefined. We compute the value of the function itself at all those critical points. We also compute fa and fb, so at the two endpoints of the interval, because the endpoints are part of the interval now. And then the largest function value that you have found from all the possible candidates, that's the global maximum, and the smallest one, that's the global minimum. So basically you look at all the candidate points, you compute the function value there, and then you decide. Because the global maximum, global minimum needs to be either at A or B, so at the endpoints of the interval, or at a critical point. So if you take all those points, all the possible candidates, and you consider the function values there, that's how you can decide. And I'm going to do an example in a little while. One more thing that a derivative tells you. If you have a function like this, so y is f of x, and as you see it goes up here and it keeps going up. It doesn't go down anywhere, it just if you go to the right it goes up. So that is called increasing. So if you have a function that is defined on some interval I, and then if you pick 2 points, x1, x2, and x1 is to the left of x2, then if you have that the function value is also fx1 less than fx2, you call it increasing. And of course, if you have increasing, you also have the opposite, the function that is going down like this, and we call that decreasing. So decreasing means that if x1 is to the left of x2, as here in the picture, that the function values then it's opposite. So then you have gone down in the meantime. So fx1, fx2. So you see that fx1 is bigger than fx2. So increasing, decreasing. And of course, there is a link to derivative here. So how does that work? Well, if you have a function like this, then if f prime of x is bigger than 0, the function itself is increasing. So the derivative f prime tells you whether a function is increasing or decreasing. So this is increasing and f prime negative is decreasing. Now, the reason I tell you this is because it helps you find local maxima and minima. So again, say that we have a function on an interval a, b, and now say that this function is differentiable. So that's quite nice, right? That's stronger than continuous, as we have seen. So a function is differentiable. It cannot have peaks and stuff like that. It needs to be somewhat smooth everywhere. Now, say that we have a point with f prime c equals 0, and that we would like to know, is there a maximum or a minimum there? Then a local, so only close to this point itself. What we can do is make a sign chart of the derivative, and that helps us. So if you have, for instance, this situation, so we have that f prime, the first derivative, goes from plus to minus. So we have a sign chart, and this is part of the sign chart. For x value equal to c, the first derivative equals 0. To the left it's positive, to the right it's negative. That means that your function is increasing to the left of c. Then it has a horizontal tangent there and it's going down again. So if you would make a little picture here, then we would have something like, well, here we have c. And then we have a function that's going up, has a horizontal tangent, and is going down again. So this is then y is f of x. And we have This is the tangent line. So since f prime c equals 0, we know that the slope of the tangent line is 0, so we have a horizontal tangent line. And you see that in this situation we have a local maximum. So that's how you can use this. So this is if you go from plus to minus in the sign chart. You can imagine if you have the situation where you go from minus to plus, that you have something similar, but now your function, your function is going down as a horizontal tangent line is going up again. And again, because we have a 0 here, we have a horizontal tangent line. The slope of the tangent line equals 0. And this means that we have a local minimum. And now there is a case 3 where f prime does not change sign, and I went plus plus here, could also be minus minus. And what is happening here is that your function itself is increasing, has a horizontal tangent line at c, and is increasing again. So this is what I sketched earlier, where you have, for instance, the function y equals x to the power 3. That one has a horizontal derivative at x equals 0, but as you can see, there is no maximum or minimum there. It's an inflection point. Okay. So let's see, how can we use all this? Now, let's do an example. So let's say that we have this function. F of x is 2x to the power 3 plus 9x squared minus 24x minus 10. And I've given a plot here, but normally you only have this formula, right? So you don't have the picture. You cannot work with the picture here. But this is just to show you how it is going and to see where we're heading there. So probably what we will find is that we have a maximum here and we will find a minimum there. Local maximum, local minimum. And it depends a little bit on the interval that you're considering this function on. It's defined for every real number. But if you look at it on an interval, then you can talk about global maximum, global minimum. If you talk about all x values, well, the function goes to infinity and to minus infinity. So if you consider it for every real number, then there is no global max or global minimum. Okay. So to find all the local extrema, we have to first compute the derivative. So f prime of x equals, well, 2 times 3, that's 6x squared, plus 9 times 2 is 18x, minus 24. Of course, I can pull out a 6. That helps a little bit. And now you probably see how you can factor this. This equals 6 times x minus 4 and x plus 1. I'm doing this wrong, sorry. I was getting a bit confused. Of course, you want to do this as x plus 4 and x minus 1. That's better. And now we see that the first derivative equals 0. That's equivalent to saying that x equals minus 4 or x equals 1. So apparently the first derivative has 2 zeros. Zeros means horizontal tangent line, so that's candidate extrema, that's critical points. So let's make a sign chart. Sign chart. So I'm plotting x here. I'm plotting f prime of x up here. something special happens at -4 and at 1, because there it is 0. To see what happens at other points, so for instance to the right of 1, this area, I'm going to plug in x equals 100. And if you do 100, you see that we have this term here, so it's going to be positive. If I plug in -100, you see that this still wins, so it's still positive. So here we also have plus. And then in between here, well, x equals 0 is in between, and if we plug in 0 here, we get -24. So here it is negative. So the function itself, what does f do? Well, if we would be looking at f, then here it goes up because the first derivative is positive. Here it goes down, and here it goes up again. And basically you see what's happening in the picture, right? Because now we see the function is going up, and then here is a horizontal tangent, so that corresponds to this point here. Then the function is going down here, that corresponds to this minus sign. And then finally it's increasing again, and that is this plus sign here. And this local minimum corresponds to x equals 1. So let's add that to our solution here. So here we have a local max with value f minus 4, and if you compute it, you will find that it's 102 at x equals -4. And here we have a local minimum f1, and if you compute that, you see that it equals -23 at x equals 1. So that gives the extrema of this function. So there is only local extrema here because we didn't specify an interval. Okay. So this is a function that is kind of smooth. You also see that if you compute the first derivative, this is a polynomial, and in principle we can compute that for every x value. It's always defined. Now, if I go here to this function, so now we have a different one. We have x to the power 5/3 minus 3x to the power 2/3. You see that you can still plot this function, or my computer can plot it, but it has a sharp pointy thing here at x equals 0. And what you also see is from the picture is that you have a local maximum here, and apparently you have a local minimum at this point, whatever it is. So let's see how we can find these if you do that by hand. So the function we're dealing with is f of x is x to the power 5/3 minus 3x to the power 2/3. Now, in principle, it goes more or less the same. So the first step is to compute the derivative. So differentiating x to the power 5/3, putting the exponent in front of it and lowering it by 1, minus 3 times 2/3 times x to the power minus 1/3. And here you see why we have this pointy bit at x equals 0. Because this term if you would plug in x equals 0, you see that it goes to infinity. So we have a tangent line, well, one from the left, one from the right, but the derivative there goes to infinity. So it has a vertical tangent line, if you like. Now, to make this a little bit simpler, I'm going to pull out the term x to the power minus 1/3, and then in between the brackets we still have 5/3 times x, because x to the power 1 times x to the power minus 1/3 is x to the power 2/3. And then the second one gives minus 2. So what you see here is that f prime x is undefined for x equals 0. And f prime x equals 0, well, that's going to happen if 5/3 x equals 2, which is the same as x equals 6/5. Now 6/5, that's 1.2. Let me quickly check that in my picture here. So that would be 1.2, that's approximately here. And indeed you see that we're going to find the correct point here. Okay. So now we can make a sign chart. So something special happens at 0 and at 6/5 for the x values. Up here I put f prime x. It is not defined at 0, and it is 0 at 6/5. And if you now compute what the signs are, so if you plug in 1,000,000, it is going to be positive. If you plug in minus 1,000,000, you get minus times minus, and this will also be plus. And if you plug in 1, then you see that you get minus here. So the function itself, f, is going up, going down, going up. And you see here we have a local maximum. f0 equals 0 at x equals 0. And here we have a local minimum. And that local minimum is f 6/5, which is an ugly value. I'm not going to compute that. I'm not interested here. At x equals 6/5. So that's the location where it is reached. Okay. So as you may recall, we have now moved to more general functions, but I started my explanation today with this little area question where you have 40 meters of fencing and you want to enclose a rectangular area and you want to maximize that. Now, that is these types of questions are being asked in 3.7 in the book. And there is a whole bunch of them. So here is one about maximizing area. and it says that a farmer wants to fence in a 3-sided area next to his barn. So barn is wherever he lives or his sheep live or whatever. But basically the idea is this wall is already there. So this wall you can use, you can build against it. You don't need fencing there. That's the idea. And then he wants to have a rectangle, so this thing here. And that rectangle is in 3 identical pans, as you see here. And each of these have identical size, and this length is y and this length is x. Okay. Now, the first question is this. Express the amount of fencing that you require in terms of x and y. So that is, of course, not so very difficult, because what you need is basically you can just count, right? There is 1, 2, 3 x's, so 3x plus, and then there is 1, 2, 3, 4 sides that have length y. So 3x plus 4y. Okay. Then the next question is to express the area in terms of x and y. Well, one pen has area x times y. So all 3 of them have this area, 3xy. Now, the question is, that's the next question. If you have 48 meters of fencing and you want to maximize the area again, how can you do that? So let's add a blank page here and try to answer this question. So we have that the available fencing, so fencing is 48 meters. And the implicit assumption is that you're going to use all of this. So 3x plus 4y equals 48. And like I did before, what I'm going to do is express one in terms of the other. And let's do it the other way around now. So let's say, well, if I have this, that is equivalent to saying that 3x equals 48 minus 4y. So I can write x as a function of y. X equals 48 minus 4 times y over 3. So if I compute the optimal value for y, then I know how I should choose x. The area A, say, is 3 times x times y. So what we get is that this equals 3 times, for x we have just found that it equals 48 minus 4y over 3 times y, which is 4 times 12 minus y times y. And let's call this thing f of y. So the notation that I used here is not important, but if I write is with dot behind it, it means this is where I define the function f of y. So I'm introducing a new function f of y, which equals 4 times 12 minus y times y. Okay. Now, I want to have a maximum of this function. So what do? I take the derivative. So f prime y. Well, if you differentiate 12 minus y, you find 4 times minus 1 times y plus 4 times 12 minus y times 1. Differentiating y. So I'm using the product rule here. If you have a product of two functions, you could also just multiply everything out and you have something with y squared and differentiate what you find then. You find the same thing. So that is minus 4y plus 48 minus 4y, which is 48 minus 8y. Which is 8 times 6 minus y. Let's make a sign chart. It's a bit much maybe here because you can immediately see how it goes, but still. X, f prime of x. Something special happens at 6 because there f prime y equals 0. And then if you take y very big, you get a minus sign. If you get it very small, you get a plus sign. So we see that the function itself goes up, goes down. And we read off from this chart that there is a local maximum f6, which is 4 times 6 times 6 is 36 times 4. It's not being asked here. 120 plus 24, 144 at y equals 6. And if you like, we can also compute the corresponding x value. So x equals 48 minus 24 is 24 over 3 is 8. So apparently the pens that this farmer is building should be 8 by 6. So that is the answer to this question. Let me see. Okay. I'm going to check the chat room for a bit. So Jana had a question about using the squeeze theorem without a graphing calculator. So the squeeze theorem, you don't have to make a picture there, right? I did make pictures when I was introducing and talking about the squeeze theorem and gave examples there. But in principle, you just give the estimate. So you just have this function g of x and you find something that is above it, something that is below it. But you don't have to give pictures there. You don't have to graph anything. You just have to give the inequalities when you do that. The midterm is going to be either Thursday or Friday, but I'm not sure for you guys when it is. It will be in Canvas. Indeed, as Fenna says, the material that you should study is week 1 up to 3 for the midterm test. Florine had a question about my previous example. The example where we have this function and y f prime of x, so the first derivative, is not defined here. As you can see, the graph will have a vertical tangent line here, so that's how you see it in the picture, that f prime of x is undefined. And then if you look at what we found here, so f prime of x is this formula, or maybe it's even nicer to see it in this formula. If you would substitute x equals 0, then this thing is nicely going to be 0, but this term here, that is the same as 1 over x to the power 1/3. And if you plug in x equals 0, then the denominator is going to be 0, and then we have 1 over 0. So you cannot plug in x equals 0 here. This is going to explode. It's going to infinity. Oh, Jan already answered, sorry. So how do you come up with functions for the squeeze theorem? So mostly in the squeeze theorem, so you have to find something that is bigger and that is smaller, right? And mostly what you see is that you have like a sine, which is in between -1 and plus, and also the cosine function is in between -1 and +1. So those are logical candidates. And what you could also have, a bit tricky, but if you would have, for instance, -1 to the power something, you know that if you do -1 to a power, -1 to the power 2 is +1, to the power of 3 is -1, so it will be -1 + 1 -1 + 1 if you do it to an integer power. So there you could also estimate the absolute value with 1, and then you have a lower bound, upper bound. But mostly it's sines and cosines. Okay. Let's see. Okay. Let us do one more example, finding these maxima minima for a hopefully interesting problem. A beer can. So let's say that we are going to make beer cans, and of course if you're a brewer, then you want to make them as cheap as possible, so you would like to minimize the amount of material that you need for making them. So here is a question, and this is one of those points where you make up a question, and then since you do not have a calculator during the exam, I mean, if you would have a calculator, I could do more realistic and maybe more interesting problems, but well, you don't, and I'm not going to change that. So here, let's say that we have a can, and the volume should be 330 cubic centimeters, so that's the normal size, right, for a beer can. And we would like to minimize the surface. So we want the surface to be as little as possible, because if we use, like, say, aluminum from a certain thickness, then if we minimize the surface, then we minimize the total amount you need for the can, and that is cheapest. So the radius of the cylinder, so here we have a circle, that's like the top and the bottom of your beer can, which has a radius of little r, and there is a height, which is h, small h. So then you can easily compute that the volume is pi r squared times h, because this thing has area pi times r squared, pi times the radius squared. The height is this, so then this is going to be the volume. It is given that the area of the side of this cylinder is 2 times pi times r times h. So that is the amount of material that you need for these sides. So basically this area, that's 2 pi r h. So the total area, and if you ever have to make questions yourself, then you realize that sometimes it's immediately clear what you want, and sometimes people wonder, if you talk about the total area, is that the sides only, or do you include the top, or do you also include the bottom here? So to avoid any confusion, this is an old test question from the final test, I think. We say this is the sum of the areas of top, bottom, and side. So let's answer that first before we keep on reading. So the total area, A. So the top. So the top has area pi times the radius squared. The bottom plus same pi times radius squared, and the side that is given plus, that is this thing here, 2 pi r h. Okay, great. So that answers the first question. The second question, we can still read it. Find expressions for r and h for which the volume is given, 330, and the total area is minimized. So we want to minimize the area, but we still have that the volume should be 330. So it seems that we have a question with two unknowns, the radius and the height, r and h. But you see that due to the volume being fixed, we can kick out one of these unknowns and we can solve for the other one. So let's see. Let's get a little bit of paper, virtual paper that is. So we have that v, which is pi r squared h, equals 330. So I am going to solve that. I'm going to express h as a function of r. So that's 330 over pi r squared. And next, what I'm going to do is, on the previous slide, I had that the area A equals pi r squared plus pi r squared plus 2 pi r h, which equals, I can take the first two together, 2 pi r squared plus 2 pi r times, and I'm going to plug in this h, so 330 over pi r squared. Okay, so I can even simplify that a little bit, and this equals 2 pi r squared. And then you see that this becomes 660, 2 times 330 over r, and the rest drops out. Now, we are going to look for a minimum here, which means that I need the derivative. So let's call this f of r. So I'm introducing a new function f of r. I'm interested in f prime, so I have to differentiate this thing. Well, that is 2 pi times 2r, so I differentiate with respect to r, plus 660 times, and the derivative of 1 over r to the power minus 1, equals minus 1 over r squared. So the whole thing together is 4 pi r minus 660 over r squared. And we see that if you want it to be 0, f prime r equals 0, is equivalent to saying that 4 times pi times r equals 660 160 over r squared. In other words, r to the power 3 equals 165 over pi. So 660 over 4 equals 165. And then r itself is the cubic root of 165 over pi. And you can now find, if you are interested, you can find the corresponding h value, the height, using this formula. Okay. So that wraps up what I wanted to talk about today. So your homework for today is to punch this into a calculator, see which r value you get and which h value you get. Compare that to a beer can and see if it's any realistic. And do the exercises, homework, visit your tutor meeting, and I'll see you on Wednesday morning. Have a great day. See you. Bye.